Hi everyone, our topic is nuclear reactions in stars. Stars, including our sun, produce energy through a process called nuclear fusion in their cores. In sunlight, stars with temperatures below 50 million Kelvin, energy is mainly produced through proton-proton fusion. In more massive stars with higher temperatures, the carbon cycle or CNO cycle becomes the dominant energy source. When stars grow older and their cores collapse, reaching temperatures over 100 million Kelvin, they start fusing helium in what's called the triple alpha process. And finally, elements heavier than iron are created through advanced nuclear reactions. From this, we aim to understand how stars live and evolve. We chose this topic because it's very relevant to modern physics. First, it explains how elements are formed in stars through fusion. Second, it helps connect physics with astronomy, like understanding supernovae and how stars evolve. It also relates to future energy sources such as fusion energy. And lastly, learning about nuclear reactions in stars helps us understand the origin of life and the future of our solar system. To prepare for this, we learned independently by discussing in our group to share and understand ideas. We also refer to our PHY310 lecture notes. On top of that, we use trusted sources like NASA, educational articles, and science channels such as PBS Space Science.
Next, I would like to discuss the challenges of nuclear reactions in stars. For the first one is high temperatures and pressures. Nuclear fusions needs extremely high temperatures, usually in the millions of degrees Celsius, to overcome the repulsive force between positively charged atomic nuclei. Next is difficulty in replicating stellar environments. The extreme conditions in stars are not easily reproducible in terrestrial labs, hindering the ability to measure and study nuclear reaction rates accurately. And the last one is low energies. Nuclear reactions in stars occur at relatively low energies, making it challenging to measure their cross-sections. Next, we also have the solution for their challenges. For the first one is stellar nuclear fusion, allowing hydrogen to convert into helium and release energy. The intense heat and pressure, primarily due to gravity, provide the kinetic energy needed to overcome the electrostatic repulsion between positively charged hydrogen nuclei, enabling them to fuse. The next one is detector investments, which is high sensitivity detectors can better capture rare reactions. Number 3 is computer simulation, which is high fidelity simulations model stellar cores under extreme conditions without physical replication. And the last one is extrapolation, which is use measure data at higher energies to estimate behavior at stellar energies. Next, we go to the concept of modern physics of nuclear reactions in stars, which is nuclear fusion. Nuclear fusion involves the joining of two or more atomic nuclei to form a heavier nucleus, accompanied by a significant release of energy. Nuclear fusion in stars in the process where light atomic nuclei combine to form heavy nuclei, releasing immense energy. Next, I would like to discuss about the importance of nuclear fusion. The first one is stellar energy. Fusion is the source of energy that powers stars, allowing them to shine and maintain their temperature. Next, stellar equilibrium. The energy released by fusion creates radiation pressure that counteracts gravity, preventing the star from collapsing. And lastly, nuclear synthesis. Fusion also plays a crucial role in the formation of heavy elements in stars, a process called nuclear synthesis. Next, I would like to discuss the facts of nuclear fusion in stars. For the first one is conditions required by temperatures of over 100 million degrees Celsius. Next, it is common fusion reaction, which is you can see in this slide. This is the most studied reaction for terrestrial fusion due to its relatively low ignition temperature and high energy outputs. The next equation requires higher temperatures but uses more readily available fuel. And the last one is basic process, which is in fusion, light nuclei isotopes of hydrogen like deuterium and tritium collide at extremely high temperatures and pressures. This overcomes the electrostatic repulsion between the positively charged nuclei, allowing them to fuse.
Assalamualaikum warahmatullahi wabarakatuh. I'm Natasha Akla binti Muhammad Azali. I would like to explain about nuclear fusion applicability in daily life. First, clean and abundance. Fusion energy could provide a virtually limitless and clean source of electricity. Unlike fossil fuels, fusion produces no greenhouse gas emission during operation and generates minimal long-life radioactive waste. This makes it an attractive option for meeting the world's growing energy demands sustainably. For instance, companies like Marvel Fusion are developing laser-based fusion technologies that aiming to deliver electricity at competitive rates by the mid-2030s. Next is hydrogen production. The heat from fusion reaction can be harnessed to produce hydrogen. That's a clean fuel that can power vessel industry and serve as energy storage medium. Current hydrogen production method often rely on fossil fuels, but fusion offers a carbon-free alternative, enhancing the viability of a hydrogen-based economy. Okay, that is desalination of seawater. Fusion reactors can generate the high temperature needed for desalination process. That's converting seawater into fresh water. This application is particularly beneficial for arid regions facing water scarcity. Fusion power desalination plants could produce millions of cubic meters of potable water daily, offering a sustainable solution to global water shortages. Last is medical isotope production. Fusion technology can facilitate the production of medical isotope that used in diagnostic, imaging, and cancer treatments. Fusion-based method could provide a more reliable and environmentally friendly supply of this critical material, addressing current shortages and supporting investment in healthcare. Okay, next, recent investment with the nuclear reaction in stars. Either will demonstrate burning plasma operation. This is operation with dominant plasma heating produced by the fusion-generated alpha particle. ITER is also developing a large part of the technologies needed in a fusion power plants. However, ITER will neither produce electricity nor will breed the tritium it uses. ITER is designed to produce 500 megawatt of fusion power and test key technologies for future fusion reactors. Next is demo. Demo will be the first demonstration fusion power plant. It's being designed to follow ITER and provide electricity to the grid. In addition to what ITER will accomplish, it will produce a net electricity output and will be self-sufficient for the production of tritium. Okay, last private sector innovations, Commonwealth Fusion System. A spin-off from the Massachusetts Institute of Technology is developing the Sparks reactor, which is expected to produce its first plasma in 2026. Sparks aims to demonstrate net positive energy output, paving the way for the ARC reactor, which is projected to deliver power to the grid in the early 2030s. Okay, let's see the potential carriers that related to the nuclear reaction in stars. Okay, first, planetary scientists. Planetary scientists that study the origin and distribution of elements in planets and meteors, often tracing them back to stellar nucleosynthesis. Next, astrophysicists study the physical process governing stars, including nuclear fusion, stellar evolution, and supernova explosion. Okay, third, nuclear physicists. Nuclear physicists investigate the fundamental force and particles involved in nuclear reaction, both in labs and in stellar environments. Last one is theoretical physicists. These physicists use advanced mathematics and computer models to predict and explain the behavior of star and stellar cores.
Today, I will talk about purpose and plan-specific skills needed to excel in the chosen career path. As you can see, the most important one is the technical skills, data analysis, which the ability to analyze large datasets, identify patterns, and draw meaningful conclusions from observational data. Second, soft skills. Communication, where effectively communicating complex scientific concepts both orally and in writing to both specialists and the public. The last one is the foundational knowledge, a deep understanding of nuclear physics, astrophysics, and related fields like quantum mechanics and relativity is essential. The next part is highlight significance of continuous self-development in achieving success in the chosen field. First, understanding nuclear reaction in stars requires knowledge of complex physics, and keeping up with current research is essential for grasping how stars produce elements, generate energy, and evolve over time. Second, adapting to new technologies, where staying current with new technologies is crucial in this field, as researchers rely on advanced tools and must continually develop their skills to use and improve them. Last but not least, let's discuss any challenges one might face in pursuing a career in modern physics and suggest strategies to overcome them. First, abstract concepts and theories. Physics use complex abstract concepts like quantum theory, relativity, and electromagnetism, which are often difficult for students to understand. Strategies to overcome. In Dubai, physics tutors help students understand abstract concepts by focusing on practical application and using personalized one-on-one teaching tailored to each student's learning style. Second, visualizing physical phenomena. Students often need to visualize abstract concepts like gravity or electric fields, but those who struggle with mental imagery find this a major challenge. Strategies to overcome. For example, tutors in Dubai use pictures, animations, and interactive tools to help students visualize abstract physics concepts, making the invisible process are more understandable and real. That's all for our discussion. Thank you.